Welcome everybody, and thank you for making our fourth monthly online webinar. And for those of you who may or may not know me, I'm Chris Wenzel, the current president of the LIPG, and thanks for coming out. So we have to do a little business before we get to the main event, and we'll take care of that right now if we can get our slides working. I think we can. Okay. The first important thing we have to do is thank our corporate sponsors for 2021. You know, without their dollars and the membership dues, we wouldn't be able to keep things going in terms of our website and insurance and you know, putting on some of these things. So we want to thank at the diamond level, Cascade Environmental Drilling, PW Grosser Environmental Engineering Solutions, and our Topaz level corporate sponsors are Alpha Analytical, EnviroTrack, ERM, Highland Pump and Tank, Regenesis, VHB, and York Analytical. So thank you. I would encourage anybody who is interested in these organizations, if you'd like to check them out, you can easily go to the LIPG website, and there is a scrolling banner with all of our corporate sponsors, and you can click on their logo as it goes by, and it will hyperlink you right to that company's website. So if you're interested, check it out. Again, thank you for all of them. Makes a big difference in how we are able to bring some of these things to you. So a little bit about upcoming events. You know, we've been doing these Zoom meetings in lieu of our quarterly dinner meetings, and they have been the third Thursday of each month. Q3 is tonight, the 20th of May and the 17th of June. We've got some bookings here on the 20th of May. I believe Regenesis is going to make a presentation on Pfas remediation, as well as colloidal reagents for CVOCs. And then we have a professor who's going to do something in June on mineral inclusions in garnets in the Gore Mountain region. And that's going to be a real good hard rocker talk. We like to blend the subject matter here, so there's something for everybody, and you know, keep everybody's interest up. We are, as usual, looking for speakers for quarters 3 and 4. We welcome all. If you have something interesting, please, you know, reach out to us. We, you know, the way we get this done is the board members are responsible for reaching out to folks and trying to, you know, get folks to do presentations. And there's so much good content out there, and it's really not hard to do. So if you can, please, you know, help us out. We're still looking, you know, hopefully at putting together some fall field trips. Those likely will be in the context of, you know, a lot of people be vaccinated, but it'll be an outdoor event in the New York metropolitan area, and likely you'd have to provide your own transportation. You know, in the past, like the Plum Island trip, we rented a bus, but I'm not sure that there's going to be a significant number of people at that time that are comfortable with that, but we'll see how it plays out, and you know, and adjust accordingly. So the LIPG is an open organization. You know, there's information on our webpage about our openness, and, you know, we're here for everyone. The board meets on the first Monday of every month, and, you know, since March of last year, we've been meeting online, and everybody's welcome. If you're interested in you know, joining us and finding out what's going on, reach out to you can just email lipgprez@gmail.com. That's on the website. The next meeting's on Monday, May 3rd. So if you're interested in getting involved and helping out, good way to meet us. One of the things that I was doing was I started looking around to see what other sister organizations are doing in the region. And it seems that most organizations have adopted some similar format. So I wanted to list here for you just a kind of a summary of what I found. And, you know, in New York State, there's several organizations. The Central New York, CNYAPG, their next event coming up is about they have a presenter talking about development of a river canyon in Chile in the northern Andes on the 21st. Hudson Mohawk, 21st also. A discussion from a professor on paleontology. The AIPG, they have on the 22nd, they have a focused remediation seminar that goes on, I think it's from about 11 a.m. to about 4. So there's a number of speakers and a number of topics. And then I was curious to see what's going on in Pennsylvania. And the Pennsylvania Council of Professional Geologists has their next 4 presentations booked. The 20th of April, there's an activity for students and young professionals. So anybody who is, just graduating from college or looking to find better ways to seek employment, this might be an interesting forum to check out. On the 27th, there's some presentation. These are all 60-minute, webinars on sample collection and lab data. 15th of June, it looks like a case study on building a dam from siting it to design and actually through construction. And then on the 27th of June, there is a discussion or a presentation on the Mars sample return program, which is part of the Perseverance rover package that is collecting samples, putting them in ultra clean containers, and it's going to leave them in a certain spot that a future mission will fly to Mars, descend, recover the containers, and bring them back to Earth. So that's going to be a good one. But I encourage you to. There's a lot going on here. And you just have to go to their websites and kind of check it out. Most of them all have a similar platform like we do for websites. So you click a registration button and you're in. I always like to put one picture for your thoughts up, and you have 2 sedimentary outcrops here. And, when I look at this, I ask myself, well, which one is Mars and which one's Earth? Or are they both Mars or both Earth? Well, kind of neat. One of these photographs is from the Perseverance rover, who's pretty busy right now on Mars. And obviously, we're looking at evidence of, a flooded basin and deposition here. And it turns out, if we zoom out, what we have is the top picture. It's Mars. The bottom picture is in Utah. So I just think that's cool. Geology has left the planet in a big way. So with that, you're probably getting tired of me. So we'll go right to the main event. And the topic tonight is thermal remediation for VOCs, SVOCs, and Pfas. And Mark Kluger and Emily Crownover of TRS Group were nice enough to volunteer to put on a presentation tonight. So please give them your attention, and I hope you enjoy the show. So I'm going to back out now, Mark, and I'm going to let you share.
Well, thank you, Chris, for inviting Emily and me to do this presentation tonight. I'm going to be talking about heating technologies. And as I mentioned earlier on, I don't know if everybody was on at the time, but my preference is people ask questions when they occur to you instead of waiting to the end. This is not meant to be a formal presentation by any means. I think it's more interesting for everybody if you ask questions when they pop into your minds. And I'm going to start the presentation this evening and talk about fundamentals of the technologies. And then Emily's going to talk about some case studies of work that we've done in New York State. And I think it's something close to 10 or a dozen projects that we've done in New York State. And I think 4 or 5 on Long Island. So we've done a lot of work in New York State, and we're just one of the thermal vendors. I'm sure the other thermal vendors have similar stories to tell about their projects. This is one of my favorite photos. This is a site in Long Island City, and what you see is Manhattan in the background. Okay, let me advance the slide. Hopefully that won't be terribly difficult. All right, here we go. So people typically consider heat an expensive remedy, and of course, it's not inexpensive by any means. Why choose heat when there's so many other kinds of remedial options available to you? And the answer is you just get fantastic results. Now, I call heat the all-in technology, that when you decide to use heat, you're really expecting tremendous mass removal reductions in concentration. In this particular site outside of Washington, D.C., we actually offered a guarantee for PCE reduction in both soil and groundwater. And you can see we guaranteed 99.9% removal. When you think about that, you start at 1,000 ppm and go to 1 ppm, and this just remarkable removal of PCE. We actually removed far more than that, 99.995%. And we did this over 4 months. So the actual project with design and construction, that takes some time, and you're getting all the necessary permits and so on. So a typical heating project from here's the notice to proceed to demobbing is usually something, I would say, anywhere from 10 to 18 months, depending on the size of the site and the complexity. And one of the nice things about heat is it works in the vadose zone, it works in the saturated zone. We don't really care what the matrix is like. It could be bedrock, it could be clay, it could be silt, sand. None of it matters. And that's really something that's unique, I think, to heating solutions. So why does it work so well? Well, actually, what's going on is a steam distillation in the subsurface. So you take water and turn it into water vapor, steam. You're getting an expansion of 1,600 times. And it's the steam that acts as the carrier gas. So you take something like clay, which is not terribly permeable, it is extremely porous, right? Clay's typically about 40% water in the saturated zone. So we're creating just a huge increase in volume when we go from water to steam. And again, we're using that steam as a carrier gas to take the volatilized contaminants up into the vadose zone, where we collect the contaminants and then treat them with surface equipment. So TRS, I'm sure, as well as other companies, offer guarantees. And I know when a vendor says we'll guarantee work, people don't really believe them. People toss around the word guarantee, I think, way too frequently. But we actually mean it. We put our money at risk. And what that does is TRS assumes significant risk. And what we find is your clients, the consultant's clients, really get a lot of benefit of, okay, so here's a vendor that's really willing to not only say they're going to reach these wonderful goals, but actually do it, or their money's at risk. Our guarantees are based on the conceptual site models that you folks are providing to us. When you think about creation of a site model, there's a paucity of data. Nobody wants to spend the money on these really super robust models. We get that. But as we're putting in our heating elements, the data density goes way up in the treatment volume. So we get to learn a lot about what's going on in that treatment zone just from installing our heaters or electrodes. So we ask that our clients be flexible and understanding, if we're going to guarantee work and right at the perimeter we're seeing DNAPL, well, perhaps there's DNAPL outside of the perimeter as well. So we have to take these things into account. And typically, we're charging 10 or 20% premium for offering a guarantee. And if anybody's interested in more details, just give me a call. We can talk about it. So when you're talking about these kinds of mass removals, 99% reduction in concentrations, I think you really have two choices. You can dig it up and take it away, or you can heat it up. And this may be surprising to folks, but if we're dealing with hazardous waste, what we're told is the cost to dig and haul is about $350 a ton, which is about $500 a cubic yard. Our pricing is typically well below that, maybe a third of that. But the caveat is if the site's pretty small, it's going to be cheaper to dig it up and take it away if you can do so. And our recommendation is do the cheapest thing that works, that meets your goals and objectives. But once you start getting to larger treatment volumes, heat in the red line here, it tends to be a lot less expensive than digging stuff up and taking it away. And I mentioned we do work in rock. This is a site that's about 100 miles north of me. I live in Wilmington, Delaware. You may have heard that there was an election recently, and our new president lives not terribly far from here, maybe 4 or 5 miles as the crow flies. And I can tell you, it's absolutely miserable when he's coming home because all the traffic in the region has to accommodate the president's entourage. In any event, we do work in rock all the time. I think we have something like 16 or 17 rock sites under our belt. And I guess you wouldn't expect to see rock in Long Island, but I'm sure you folks do work all over the place. So heating technologies, there are 3 main technologies that are brought to bear in the subsurface: thermal conduction heating, resistance heating, and steam-enhanced extraction. And this slide, I think, is a little confusing. It's meant to depict that you can use conduction heating through this entire range, while resistance heating and steam-enhanced extraction is more limited. And so that begs the question, if conduction heating will work on everything, why even consider the other technologies? And the answer is, if these other technologies will work, they are likely to be less expensive than conduction heating. So conduction heating is just a great solution for semi-volatiles, including Pfas. Whereas resistance heating and steam is going to be focused on the more volatile constituents. Hepa remediation, this is a term that we use internally at our company, is essentially applying heat at sub-steaming temperatures to increase naturally occurring processes, such as bioremediation. We see reductions in concentrations at our sites even after we pack our bags and go home. So that's sort of unusual, right? You have a vendor that implements a remedy, the vendor goes away, but concentrations continue to go down. Well, and that's because we've made life really cozy for some of the indigenous microbes. So I went through a lot of stuff pretty quickly. Does anybody have any questions at this point? Okay, I'll take silence as a no. By far, the 2 most applied technologies are conduction heating and resistance heating. And that's because of the fantastic results that you get. With steam-enhanced extraction, it's mainly a NAPL mobility issue. You're typically used in transmissive aquifers for LNAPL recovery. So this is what a steaming site looks like, or resistance heating or conduction heating looks like. We take municipal power, it goes into this gray box, we call it a power control unit, and it steps down this voltage, that's what, 13,000 volts, something like that, and applies that voltage to wells in the subsurface. And we have 2 different types of wells. In the case of electrical resistance heating, these are actually electrodes. And we're not heating the electrodes. The electrodes essentially communicate with each other, and the formation completes the circuit among the electrodes. And it's the soil matrix itself that acts as a resistor, and the resistor slowly heats up. And when I say slowly, it's not that slow. It's perhaps 1 to 2 degrees Celsius a day. So in 4 to 6 weeks, we're at steaming temperatures. So what we're trying to accomplish here is a phase change. We're taking the liquid phase or the sorbed phase contaminants, putting them into the vapor phase. We're evaporating them. And as I mentioned earlier, the steam that we create carries these vapors into the vadose zone, where we have vapor capture, and then we have a treatment train at the surface Typically, we're using activated carbon, but if we have a lot of mass, we often use thermal oxidizers. So all this equipment at the surface is what we bring to the site, and we operate all this equipment. So fundamentally, it's a pretty simple process. We're injecting electricity. The formation is the resistor. It heats up and volatilizes the contaminants. In the case of conduction heating, we're actually heating up these individual wells, and we call them heaters. And these heaters can get to temperatures, around 800 degrees Celsius, and that is smoking hot. And the heat front propagates radially away from the heaters. The maximum temperature of water is its boiling point. And in the case of resistance heating, we have to have water or moisture in the vadose zone in order to conduct electricity, which means that with resistance heating, the maximum temperature you can achieve is the boiling point of water. With conduction heating, these heaters get super hot and this wavefront propagates away from the heaters. It's going to evaporate all the water in the vadose zone. And once all that water is evaporated, then we can get to very high temperatures, up to 400 degrees Celsius in the vadose zone. The saturated zone, that's going to be more difficult, right? Because it's wetter, right? And it's recharging all the time. So unless you are dropping the water table, the maximum temperature you can achieve in a saturated zone is the boiling point of water. Right? So that's an important distinction between the two technologies. So how do we at TRS figure out which technology to use? Well, we have a proprietary model. We take the conceptual site model that you folks have provided to us. We try to understand your goals and objectives. And that model informs us of which technology will be the low-cost solution. The model also optimizes the power inputs and the energy densities. And I'll talk about a little bit more about these. But power density and energy density is what gets your site clean. So energy is power times time. So if we're talking about power as a function of time, that's how you get energy. So we're going to take a look at the contaminants that you have, what kind of reductions you're looking for, subsurface conditions like groundwater flow rates, the type of stratigraphy or lithology that you have, and we plug all these things into the model. So power delivery ends up being super important. If you have insufficient power delivery, the heat losses you won't be able to overcome the heat losses at the site. So the goal here again is typically to get to steaming temperatures. If your heat losses are high enough, you'll never get to steaming temperatures. So now we're in the weeds a bit. If you ever reach out to the vendors for a proposal, you're going to get these really well-crafted proposals, and they're all going to be different, and it's going to be hard for non-experts to really figure out which is the best value. We encourage you to look at power density and energy density, and the number of heating elements that you have in the treatment volume is a good proxy for power delivery, for power density. And the units here would be kilowatts per cubic yard. Now, it might be a bit surprising, but with resistance heating, we can actually deliver power at a faster rate than with conduction heating. And to me, that's not terribly intuitive because conduction heating actually gets to higher temperatures, as we discussed, but you can get more power in per unit time with resistance heating. And again, for those sites where resistance heating will work, that's a key reason why resistance heating is less money than conduction heating. And we pay a lot of attention to power delivery, and we have all sorts of fancy algorithms in our delivery systems to make sure that we're doing a good job optimizing power delivery. It's energy density that allows you to achieve your goals. So this is maybe a little weird on the y-axis. This is the amount of contaminant that's remaining as a percentage. So 1 would indicate 99% concentration reduction. 0.1 would be 99.9. So this is logarithmic, as you can see. So PCE is not as volatile as TCE. So the energy density required to achieve the same remediation goal is greater for PCE than it is for TCE. And this sort of makes sense. This is rather intuitive. But look at two isomers of TCA, trichloroethane. The boiling points are way different for these isomers, and this surprised me. So there's a huge difference here in the energy density that's required for the same percentage mass reduction. And so this is kind of stuff that TRS looks at when we're coming up with a remedial approach and pricing for your site. So I mentioned this a little bit earlier, that even when we go home, concentrations continue to decline. So here we're showing in yellow what the concentrations are when we show up. Red is when we flip the switch off, and black is, a year and a half, 2 years later. So something's going on at our sites that allows the remedy to keep on working. And primarily, this is an effect of bioremediation. And this works great with the chlorinated ethenes. If you have the right microorganisms there and a food source, you can get a continued reduction in concentrations of the TC, PC, and so on. But there are other naturally occurring processes that occur in the subsurface, some of which are abiotic. An example of that is constituents, energetic compounds like RDX, which is an explosive that was used extensively in World War II. Hydrolysis is a water-based reaction. Water is the reagent. And because water is the reagent, and because water is everywhere in the subsurface, I don't have to move the reagent to contact the contaminant. They are already in contact with each other. So this is way different than adding a bioremediation substrate or a chemical reductant or a chemical oxidant where it's a contact sport. People talk about contact sports. Here, we're already in contact. Even in clay, right? Clay's not permeable, but it sure is porous. And so if a compound hydrolyzes, then this methodology could be very effective. All we got to do is raise the temperature. We can do this at below steaming temperatures, so vapor capture and treatment go away. And we just have this abiotic reaction, and the kinetics are modulated really based on temperature. pH also, but it's hard to change pH in the subsurface. It's easy for us to change temperature. So here's a site in Nebraska where we went after these explosive compounds, and you can see there's no vapor capture here. We're just treating this cell, and this was a huge success. We did this for the Omaha district of Corps of Engineers. So with steam, I mentioned that TRS also does steam injection. We are injecting steam, we're pulling out through multi-phase extraction. Well, as I mentioned earlier, we're primarily using steam for the mobilization of NAPL and transmissive aquifers. But there might be application just to inject steam in systems where you have high groundwater flow, because we can easily affect the temperature in that high flow regime with steam. So it's a way to improve the performance of perhaps conduction heating or resistance heating. And this is what a steam site looks like. Again, we have a boiler here at the surface, and we're injecting and extracting, we're injecting steam and extracting water, contaminants, and steam. For our conduction heating, we are putting essentially a wire in a pipe, in a steel pipe. We flip the switch, and this wire gets incredibly hot. Again, perhaps up to 800 degrees Celsius. That is warm. And we can do this in small diameter casings. And that's a nice thing because we can lower our drilling costs. And at TRS, we've got a really robust R&D group. And we've heard recently that the US Patent and Trademark Office is about to grant us a patent for our heater design. And the major vendors know how to do this. All the vendors are good at energizing heaters. There are nuances, but we could talk about that some other time. This is one of our sites in Fort Smith, Arkansas. This is, you know what, I'm not sure how many heaters we have on the site. It's something like 200 heaters. I'm not sure the exact number, but you can see TRS has done a number of heater projects, thermal conduction heating. We grew up doing resistance heating, but the conduction heating part of our business is growing very rapidly, and that's a nice thing. And we have 2 projects that are funded by the Department of Defense. These are their pilot study research program, ESTCP, and both of these projects are for PFAS, which I'll talk about in a little bit. This is a site not terribly far from you folks in northern New Jersey. It's at a Superfund site, and we're putting in something like 4 linear miles of heaters. This is the biggest project TRS has ever done in the United States. It's huge for us. It's very complicated drilling. We're almost finished with the drilling program, and we're about to construct the surface equipment. Here's a power delivery system with all these cables going to the heaters. So this is a real success story for TRS. This is a resistance heating site. You're looking at about 20% of the electrode field. You know, we've got lots of blowers, condensers, and so on. All this stuff at the surface is our equipment. These step-down transformers allow us more control putting energy into the subsurface. Here's a site in Long Island City. This is the very first photo that I showed you was taken at nighttime from the roof of this building. You can see how complicated an implementation would be under this building, and that's exactly where we're doing our work. This is a completed project. This is now a tennis club on top of the roof of this building. The subway line, I think it's the number 7 line, if I'm not mistaken. The roadway here had to remain open in case of a terrorist attack, and the city wants to move lots of people. We actually had our equipment on trailers with wheels, so they could easily be moved away. It's a very, very interesting site. I mentioned we have a robust R&D program. We've got patented technologies for 1,4-dioxane and other miscible compounds. And we have a patent actually on thermal remediation of PFAS. So PFAS is all the rage these days. Certainly TRS is paying a lot of attention to it. We have 3 awards from ESTCP for PFAS remediation, and each of those projects are slated to start in 2021. We were awarded these projects over a year ago. So we're doing work for heat in the vadose zone and also ex situ soil piles. It turns out that the military has lots of construction waste and all this contaminated soil, and they don't know what to do with it. So we're going to essentially take those soil piles and heat them up, volatilize the PFAS. So PFAS boiled, I don't know, was it 10,000 or so different type of PFAS compounds. They all seem to boil, most of them below 300 degrees C. And as I mentioned earlier, we can get to much higher temperatures. But it costs money to get to higher temperatures. So if, for example, I was going to go after PFOA or Pfas, you would think you could do so under 300 degrees C. So it turns out that we did some experiments, and at 300 degrees C, we did not get very good mass removal. I mean, it's not terrible, but it's not what we need to get to. But at much higher temperatures, you can see what kind of mass removals we got. They're just outstanding. So at 400 degrees C, it's practically 5 nines mass removal. That's amazing, right? And at that temperature, we suspect, we don't know yet, but we don't think we're breaking down these compounds, but we're working through the ESTCP program for mass balance, so we can actually see what's going on as we're heating up these sites. So but this is exciting for us, for our clients, that we can remove these compounds from the vadose zone or from ex situ soil piles. And with that, I am going to pass the baton to Emily, who's going to talk about the projects that we've done in New York State. Emily, do you want me to move the slides, or do you want to share your screen?
Yeah, that sounds great. If you want to progress the slides, I can always switch over if we need to.
Okay.
But yeah, no, thanks, Mark. That was great. And I did want to just add on a little bit to the PFAS remediation. That previous graph or figure that Mark showed, where it showed the different PFAS constituents. In general, if PFAS are smaller molecules, they boil or are removed, volatilized at lower temperatures. So even if PFAS are broken down, they would be broken down into smaller molecules, and those would be able to be remediated at the temperatures that we're achieving. So it's not a bad thing if they are broken down, and it would be something that would still be removed with our temperature at our target temperatures.
We actually do have a question if you guys would like to take it right now.
Sure.
Yeah.
Okay, it comes from, and I hope I pronounced your name correctly, Xuan Xu. How is the vapor collected and treated for PFAS after heating?
Yeah. Mark, do you want me to answer that, or would you?
Yes, please, go ahead, Emily.
Sure. Yeah. So essentially what we have is we use a blower to apply a vacuum to either the subsurface or an ex situ soil pile. And essentially that provides capture of any vapors or steam that are generated. We use a scrubber to transfer the majority of the PFAS in the vapor phase to a low volume water solution. And then we pass the vapors onto carbon through adsorption. And then a small amount of water that's generated, we also use carbon to treat the aqueous phase as well. But essentially we separate we try to preferentially transfer the majority of the PFAS to the aqueous phase. And then we have a small amount in the vapor phase that's treated through carbon at the surface. Did that answer your question? Perfect. I just saw the chat.
That does answer it. Thank you.
No, and so, oh yeah.
It's Chris Wenzel. I just had a couple of quick questions on the technology before you get into the case studies. And Mark, when you were showing one of the energy density slides, I saw in the list of things to consider TOC. I'm assuming that's total organic carbon, and it's a factor in determining the stubbornness of compounds to mobilize because of their affinity for carbon. Is that right?
That's exactly right, Chris.
Okay.
And that's why we use carbon for filters, right? Because it has essentially the van der Waals forces, or
Right.
It takes more energy to remove the contaminant from the carbon. So it's not a showstopper by any means at all. It's just factors into the price of the remedy. We have to run the system longer to achieve the goals.
Okay. And then obviously we all know that there are bacteria that can live at very high temperatures on the planet, but I don't know the particular affinity for good chlorinated solvent eating bacteria to survive temperatures, but I would think that those temperatures would sterilize the ground.
Yeah, so
the matrix.
It's an interesting comment that you make, because initially the researchers at TRS thought the same thing, that we would be sterilizing the bacteria that we like, from the site, but it turns out that that's not the case. In the case of the chlorinated ethenes, the bug consortium that we like includes a bug called D. helicoides.
Yep.
D. helicoides seems to thrive with its metabolic rate for the respiration of these compounds. Seems to be highest right around 35 degrees Celsius. And D. helicoides sort of shuts down somewhere between 40 and 45 degrees Celsius. But we don't think we're killing it when we get to boiling point. So what we see happening is, as the site cools down to temperatures below 40 degrees C, the bioactivity just accelerates like crazy.
Okay.
So your point's a good one. We thought the same thing, that we'd be killing the bugs, but we're not. At every site where we have chlorinated ethenes, we see this effect, that concentrations continue to go down.
Okay, thank you.
You're welcome. Okay, Emily, next slide, Emily.
This one's perfect.
Okay.
As Mark mentioned, TRS has completed 10 projects across New York State. So this is just showing a map of where we've remediated sites, 4 of which are on Long Island. And yeah, if you go to the next slide, this shows a list of all of the projects that TRS has implemented in New York. So you can see a range of contaminants, from chlorinated solvents to fuel-based contaminants, and a range of goals, both in soil and groundwater, and also vapor concentration goals.
Yeah, right here.
Yep, asymptotic vapor, which we do have a site as an example where essentially it helps you determine the, how you're applying thermal remediation most efficiently. So there are diminishing returns where you start extracting a lower amount of mass the longer you treat. So in that site's case, it allows us to monitor for that and help us most efficiently apply thermal when it's the most impactful. So that's the first site example on Long Island that we're going to share today. We recently completed this remediation. This is Matisse Petrochemical Superfund site. So it was in Glen Cove, and it was previously a chemical blending facility. So that blending took place between the mid-1960s and the mid-1980s, and it resulted in widespread SVOC and VTEX contamination on the site. And if you go to the next slide, based on the varying contaminant profile across the site, the thermal treatment area was split into different zones. And each of these zones, they were monitored independently for mass removal. And that was due to the highly variable contaminant mix that was present across the site. And we used asymptotic mass removal as the regulatory remedial goal. So essentially, we were monitoring each zone independently and using analytical sampling to detect which contaminants we were removing and the concentrations of those contaminants in the vapor stream. And essentially, we were able to find for each zone at what point we had reached diminishing returns for those zones, at what point we were extracting most of the mass, and there was very minimal mass that was being extracted. And that's what was the prompt to de-energize each zone. And across the site, we installed 155 electrodes to reach the goals. And if you go to the next slide, there are multiple indicators that can be used for remediation. So the asymptotic vapor was the contamination-based remedial goal. But as Mark described previously, there are a number of other factors that go into how we can detect and know that we've reached the goals and applied thermal remediation to the best extent possible. And the electrical energy is one piece of that. So as Mark described, we perform a thermal model for every site, and we evaluate the energy needs. So we look at what is the steaming energy density that we need to apply. It's very contaminant specific. It's dependent on the site geometry, how much surface area it has, heat losses, and that all goes in until it goes into output a final predicted energy. And so we use that to monitor at what point we predict based on our modeling that the remediation would be complete. We also use temperature. So this site also had a temperature specification. The idea and the intent was for source removal. So we were looking at the temperature specifications were based on the contaminants that were the primary contaminant concern in those zones. And there was a temperature specification based on those contaminants. And then we also look at the mass removed. So in this graph, it's showing on the right-hand side, the cumulative mass removal that's shown in the orange curve. And you can see the site we removed over 10,000 pounds of mass. And then on the left-hand axis, that's the mass removal during each reporting period between sampling events. And that curve is represented in blue. And you can see that the majority of the mass was removed early on in the remediation. So you can see those peaks there, and then it trails off and you start seeing diminishing returns overall on the site. And that's shown on the far right-hand side. And you can see that the peaks and valleys that are occurring in the middle, that is a function of how the different zones were heating up and the different contaminants that were observed at the site. So some of them were much more volatile and the extraction, and we could see this in the analytical results, but we could see some concentrations of different contaminants being extracted very early on, and then they would taper off, and then we would see another influx of a different contaminant that was observed in the different zones. So it was a really interesting site, and just an example of how you can use vapor concentrations and then a mix of energy and temperature to determine when is the optimal duration for your thermal remediation. The next site is what took place in Edgemere, New York. It was just south of JFK. And if you go to the next slide, this site was bordered by a strip mall to the north. It had commercial properties to the east and the west, and then it had a road or a freeway to the south. And there was also an elevated railroad and residential apartments that were near this site. 36 electrodes were installed. And you can see in terms of the pattern of the electrodes, those are represented by the red circles. Those each represent an electrode, or they could represent a heater if it was a TCH site. But essentially, they're to most efficiently heat up a volume, we place them in a triangular pattern. And that both for ERH and TCH, that results in the most efficient way and to heat up a site. At this site, TCE was the primary contaminant of concern. And if you go to the next slide, this is showing our groundwater results. This was the remediation goals for the site were both soil-based and groundwater. The soil goals, we actually were below detection limits in all 12 soil samples that were collected. For groundwater, you can see these are the different wells that were sampled. And on the y-axis, this shows the TCE concentration. And just want to note that this is a log scale. We use that just so you can see when we see such significant reductions, it helps us see that those lower concentrations, just how much it varies. It just gives you a little more detail when you're looking at the reductions we achieved. And what we observed is that even 5 months after we had completed heating at the site, we had still achieved a 99.8% reduction for the TCE goals. And you can see the remediation goal for TCE that's shown in the red line. And early on, even at 100 days of operations, 3 of the locations were below that goal. And then we were able to get below that goal through the remainder of the remediation. The third case study was a site that TRS completed in Rochester, New York. It was at a manufacturing facility that was constructed in 1968, and TCE was used at in this facility for their manufacturing process. So they used it to remove perforating oils. And the highest TCE soil concentration at this site was 2,200 milligrams per kilogram. And it also had daughter products as well that were contaminants of concern. But the remedial goal for TCE was 0.47 milligrams per kilogram at the site. This is showing a layout of the electrodes. The treatment area extended across a 10,000 square foot footprint. And this site had sheet pile electrodes as the primary electrode on the site. And sheet piles are another form of electrode that can be, in some circumstances, if the site has the right characteristics, it can help reduce costs in a number of ways. So sheet piles, you can essentially drive a metal sheet pile into the ground. It helps reduce soil waste that's generated. And it also, because it has such a high surface area, it allows you to have the electrodes at a wider spacing. So you have less electrodes that need to be installed, which further reduces the cost. We do a site evaluation for all sites to see if they're a good fit for sheet piles. Not all of them are, unfortunately, but it is something we always look at because it can help really reduce costs. And if you go to the next slide, this just shows the mass removal at this site. We removed more than 2,500 pounds here, and also shows the temperature curve and kind of the correlation. You can see the bulk of the mass was removed early on, and then you saw a diminishing removal as we achieved higher temperatures. And that's just a kind of a quick snapshot of sites. There are a number of other site examples we could provide for you if you guys have interest. We also have, if you're interested in us running a model for a site, they're very quick for us to run. We have just a quick site evaluation form that you can fill out with some key parameters. And then we can output the predicted energy and a quick overall design of what that might look like. But yeah, with that, Mark, I think I'll pass it back to you.
Yeah, we're at the end here. Thank you, Emily. The key points are we've done lots of work in New York. We've got PFAS solutions these days. We encourage you to really pay attention to the power and energy densities. Guarantees are something we routinely offer. So as Emily said, we're happy to discuss with you any of your sites where heat might make sense. And we understand that most sites are not going to support the cost related to using heat. People are doing other things that cost less, but they don't get the same kinds of mass removal or concentration reduction. So like everything in our business, all depends on your goals and objectives. And if anybody would like to chat with Emily or me later on, here's our contact information. And with that, Chris, I will pass it back to you.
All right, thank you, Mark. This is probably a good time to, if anybody has any questions, now would be a good time to start that dialogue.
Mark and Emily, it was a great talk. I really excited by this concept. What could you please describe the sheet pile application?
Yeah, so as Emily indicated, we actually rate sites for sheet pile goodness. And what that means is the challenge that we have with putting energy into the subsurface with electrodes is that we tend to dry out the interface where the electrode meets the soil. So in the saturated zone, that's not an issue at all. But in the unsaturated zone, the vadose zone, we have to make sure that we keep that intersection, if you will, or that contact point moist. And that's a way easier thing for us to do with bored electrodes than it is with sheet piles. So if we have a large vadose zone that's sort of dry to begin with, it's probably not a good site for sheet pile electrodes. But if we're doing our work in the saturated zone and it's a shallow vadose zone, that's a great application for sheet piles. And these sheets, I believe, are 48 inches wide, Emily. So we just bring over this big equipment and drive the sheets in. They go in remarkably fast. There's no IDW. We love them if we can use them. And so, as Emily indicated, we look to use them at every site if we can. Brian, did that answer your question?
Yes, it did. Thank you.
Okay.
Another question, if you don't mind. I saw you did Long Island City. One of my concerns when I first saw it was how are you going to handle infrastructure and all these other things like foundations that could be in the way. And it seems like you get the same results going across a building footprint. And the foundations where things might accumulate don't seem to be a problem.
No, so I would say that we're under infrastructure, buildings, roads, railways, probably something like 75% of our projects. We do work under buildings all the time. We can put in heaters or electrodes at angles. We can, in the case of that Long Island City project, we actually disassembled the drill rig, took it down the freight elevator, reassembled it in the basement, and cored through the concrete foundation and put in our electrodes. So there's usually a solution. Of course, we'd be concerned about vapor intrusion, these kinds of things, but we do this stuff routinely. And we work very closely with the consulting engineers, geologists. Everybody has to be on board, including the regulators. We want to come up with a solution that makes sense for all the stakeholders. So we work really carefully, cooperatively with all the parties.
Hey, Mark, it's Chris again. What has been the deepest application that you folks have seen success at? And I'm curious if there's well, let's say I have a vertical thickness that I have source material throughout that thickness, so I want to attack it from that perspective because maybe I had a free phase napple that moved down. Does the length of the electrode, is there a terminal length where you just can't get enough electric in there and heating, or how's that work?
Yeah, no, the answer to your question is no theoretical limit, Chris, to how deep we can go. And I believe the deepest wells have gone, or electrodes were 135 feet. That site that I pointed out in northern New Jersey, that Superfund site, our heaters, I believe, are more than 200 feet long, but they're put in at rather shallow angles. So it's not quite as deep, but the heaters themselves are quite long. So no, there's no theoretical limit. There's of course an economic impact, right? The the single most important element that drives cost is treatment volume. And that's probably true for any treatment methodology, certainly true for heat. So I would say 90% of our projects fall into the range of $1 to $10 million. We have very few that are less than that. We have more sites that are more than $10 million than sites that are less than $1 million. And we're looking at some really large projects right now as we speak, specific to PFAS soil piles. And we're looking at one site where it's something close to 150,000 cubic yards of soil that's piled around an Air Force base that we're hoping to heat up. Yeah, so to answer your question, there's no theoretical depth limit. The deepest we've gone to date is 135 feet, but we certainly could go deeper.
Thank you.
Okay, and we have another question in the chat from Derek Erzbach. Is there any issue when a site is near a geothermal system?
What concerns us typically regarding infrastructure at a site is that we don't drill through something. We're not the drillers, right? We hire the drillers. So that's the first thing. We have to make sure that we're not drilling through anything that's important. The other thing that we are concerned about is any PVC in the matrix. Usually the PVC are for monitoring wells, but if there were other reasons for PCE to be there, that would be problematic. You'd have to abandon it. PCE gets sort of gooey around 60 degrees C. And as I indicated earlier, we're going to the boiling point of water. So, I don't see any real issues with geothermal wells as long as we don't, penetrate them with our drilling program.
I guess to kind of follow up on that, like, do you have an idea of how far out your radius of influence is for the heat to?
Absolutely. That's something that we pay close attention to, and it's captured in our heat wave model. Now, Emily, I'll pass that question on to you.
Yeah, it's site specific. And for instance, if there were sensitive, like Mark was describing, we commonly treat around different subsurface features like utilities. And if there's anything that's within a certain proximity of the site, we perform a site specific thermal penetration model just to ensure that we won't have any elevated temperatures that might risk the utilities. And we can install cooling loops if required to protect it. So we've treated around high voltage subsurface, high voltage electric lines, fiber optics, water lines, natural gas. And we just, we do the thermal penetration modeling and evaluate each site and, apply the appropriate measures to protect them.
Thank you. We have another question from Eric Weinstock. Do you have a table that lists the type of data you need to evaluate a site?
Absolutely. If you go to our website, thermalrs.com, you can see it right here. You go to the Contact Us button, and it'll bring you right to our site evaluation form. Probably take, 20, 30 minutes, something like that, for you to fill out the information. And then it goes to our engineering group, and we do an evaluation for you. And we typically, for a ballpark estimate, which is usually how these sites start, we can provide that information with just in a few days. We try to be really responsive. And when I say ballpark estimate, it's usually within, perhaps 20, 30% of what the final price is going to be. And I guess I would be remiss if I didn't mention that if you place an order while the presentation is occurring, you get a discount.
And I have a question. Is there some kind of insulation that you use at the surface?
It depends on your goals and objectives. If, in the case where we're really going to very high temperatures, perhaps the heat loss at the surface would mandate that we put in some sort of thermal cover. For most of our resistance heating sites, we don't have thermal insulation at the surface, but sometimes we do. It's site specific. And again, we're trying to provide a low cost solution. And so we model the sites to use energy most efficiently. And sometimes that means that we're going to put a thermal cap on the site. Sometimes we don't have to.
So the heat doesn't make it to the surface? then? The heat stays?
Earth materials are
Hello?
really good insulators, right? So it's not usual that we heat right to the surface. We can, of course, but that's usually not what we're doing. So if you were heating right to the surface, yeah, we would have some sort of thermal cap. But usually we're starting to heat 3, 5, 7 feet below grade, something like that, maybe more. And in those cases, the further you are from the surface, the less the requirement is to have a thermal cap. It's site specific.
Gotcha. Okay, thank you.
You're
And
welcome.
when we run the analysis for each site, we look at the R value for the thickness of the soil above the treatment volume, and we can look at the predicted heat up rates for each volume. It looks at the geometry of the site, and that goes into it. And then if it does look like we want to have an insulative cover on the surface, there are different types, and it'll depend on the site too. We can use polyisocyanurate foam board, we can use aerated concrete. There's different options depending on the site's needs.
What
Okay,
about,
thank you.
and what about having to cover the surface to convince regulators that you're not going to generate uncontrolled vapors in a residential setting where they either say you have to put a sprung structure over the remedial area or you have to cap the remedial area from that perspective? Have you encountered that?
The short answer, Chris, is people ask these questions, and then we
Yep.
talk to them in detail about our experience and our modeling and what we expect and all the sampling that we're doing. Oftentimes we'll have 24/7 sampling at sites. So generally, we're not required to build these sprung shelters, if you will, or structures.
Yep.
Emily, can you recall any time where we had to build something? I can't think of any.
And really the nature of it is we're applying a constant vacuum on the subsurface. So we are collecting any vapors that are generated, and we have safety interlocks in place for our system. So if there were ever to be a disruption in that, in that vacuum that's being pulled for ERH sites, the electrodes would immediately be just de-energized, and that would cease the active boiling of the remediation. So that's a safety interlock for ERH sites that, can, if there are concerns by the regulators, that's a lot of what we do is kind of go through the risks and show them what risks really do exist for the site.
That's a good answer.
And we can also bring backup generators if people are really crazy about it.
Do you recall any specific concerns that have been raised by regulators in New York?
I would say the concerns in the regulatory community are not state specific. It's the kinds of things that we're talking about. Are we going to damage subsurface infrastructure? What are you doing for vapor recovery? People ask questions about the permitting process. And so we have to date domestically something like 160 projects under our belt. So we've done this a lot in the United States. Actually, we have a worldwide footprint. We have joint ventures in South America, China, and in Europe. So we're doing this work all over the globe, but most of our work has been in the United States. And I don't want to make it a commercial for how wonderful we are, but we work really cooperatively and collaboratively with the consulting firms and the regulators to make sure their concerns are addressed.
All right, sounds good. We have another question from Eric Weinstock. Can the system be placed in an active parking lot?
Absolutely.
And essentially for instance, the electrodes can be installed below grade, and it allows you actually wouldn't even know that you were walking on top of a below grade site. We have trenching, all of the pipings under an asphalt covered surface. So we have a number of sites where it's been below grade and in active parking lots where there's foot traffic and there haven't been any issues.
We've done work at universities.
Yeah.
and all the students survived.
All right, I think last call for questions, anybody?
Well, thanks again for inviting us. It was way fun.
All right. Yeah, thank you. That was a very most excellent presentation, Mark and Emily. And we really appreciate you coming out and doing this. So thank you.
You're welcome.